very nicely to our next session, which is on resiliency, debugging, and trust. So we have 4 great papers in this session. And kicking things off is Jingju He. She is a 5th-year PhD student at North Carolina State University, and she will graduate in this coming year. She's on the job market now and interested in both academia and industry jobs. So you can contact her if you have suitable job opportunities. And I think we have all 4 speakers. So, okay, let me share my screen and then you can take it away. Okay, hopefully that's showing up. You can go ahead.
Can you hear me now? Hello? Can you hear me now? Yeah, thank you for the introduction. Today, I'm honored to give this lightning talk. I will present Hang Fix. Hang Fix is an automatic software hang bug fixing tool for production cloud systems. I'm Jingju He from NC State University. This work is collaborated with Ting Dai from IBM Research, Helen Gu and Guo Liangjing from NC State University. Can you turn to next page? Software hang bugs are difficult to diagnose and fix due to the lack of debugging information. Even if the developers can detect that there is a hang bug, it is still difficult for them to come up with an effective patch. Therefore, we propose Hang Fix. Hang Fix is a domain-agnostic, bytecode-based hang bug fixing tool. Hang Fix takes the application bytecode and bug triggering test case as the input, and Hang Fix produces the patched application bytecode as the output. Hang Fix consists of 4 steps. The first step, hang function localization. Hang Fix leverages the stack trees to pinpoint the hang function. Next, the next step, the likely root cause pattern matching. Hang Fix matches the hang bug to a set of commonly seen root cause patterns. Currently, we target 4 likely root cause patterns: the unexpected function return values in loops, misconfigured parameters in loops, improper exception handling in loops, and blocking operations without any loops. The first 3 patterns are related to infinite loop, and the last one is related to blocking operations. Next, Hang Fix produces the patch based on the identified root cause patterns. Hang Fix adopts very simple strategies to enable the system to jump out of the stuck state. Specifically, Hang Fix throws the exception, restores the default value, traces execution of loop updating, and adds timeout checking to fix the 4 likely root cause pattern correspondingly. Lastly, Hang Fix validates the generated patch by rerunning the existing hang bug detection tool, rerunning the hang function localization tool, and runs the application's regression test suite. If the hang bug does not occur again and all the regression test suites are passed, then we consider this patch is valid. Can you change to next slide? Here comes our evaluation results summary. Our evaluation consists of 2 parts, an empirical study and an experimental evaluation. Our empirical study is done over 237 real production hang bugs. The results show that 76% hang bugs fall into Hang Fix 4 likely root cause patterns, and Hang Fix can fix 75% of those bugs that fall into the 4 root cause patterns completely. We have conducted experiments over 42 reproduced hang bugs on 10 cloud server systems. Among the 42 hang bugs, 14 bugs have been fixed by developers and 28 bugs still remain open. And Hang Fix can fix 40 of them completely. Thank you for the audience, and I would be happy to answer any questions.
Okay, great, thank you. One request for the questions: if you are asking a question during the talk, please use the Zoom Q&A. Don't post them on Whova because there's a bit of a delay. But let me check Whova first for any questions in advance. No, it doesn't look like we have any here. Okay, so while people are typing in their questions, maybe I can ask a couple. So one question is, can you tell us a little bit about how you distinguish between a hang bug and just lack of progress due to a live lock, for example, or a deadlock?
Oh, that is a good question. We actually, this hang fix focuses on hang bug fixing rather than hang bug detection. So hang fix will apply some existing hang bug detection tools to do hang bug detection. For example, our previous work, T-scope and D-scope can detect the hang bugs caused by timeout issues or data corruption issues. Also, there are some existing detection tools to detect like data lock bugs, as you mentioned, but it is not our focus in this paper. We know that these hang bug detection tools can have some false positive rates, but it's out of scope of this paper.
Okay, and can you tell us a little bit more about the limitations of this approach? What are the type of bugs that it might not be able to do?
Okay, we talk about that in our empirical study. Among the bugs that fall into the 4 likely root cause patterns, there are still 25% bugs that cannot be fixed by hang fix. It is because to fix those bugs completely, we need to insert some application-specific functions, or we need to restore the system state. For example, I talked about there are 2 negative cases in our experimental evaluation. To fix these 2 bugs completely, we need to restore the corrupted data. If we cannot restore them, restore the data, and it will cause some new problems in the later execution. So hang fix is used to fix hang bugs on stateless systems.
I see. Okay, great. So Ting is asking, what will be the future work of hang fix? What is next?
Oh yeah, the future work of hang fix. Currently, we are thinking that because these the hang fix currently produces the patched bytecode, and we can transform the bytecode patch into the IR code patch for the developers to check. But it will be easier for the developers to check the source code patch. So we are considering that whether we can transform the IR code patch into the source code patch and for the developers to check them.
I see, great. So Brian asks a question that is related to what we were talking about before. So he says, interesting work regarding the other 24% of bugs not fixed by hang fix. What kind of bugs are they?
What kind of bugs are they? They have various root causes, so I cannot give you a detailed categories of them. So I conclude that they to fix them, we need to insert application-specific functions, or we need to restore the system state. I can use another example to illustrate it. For example, in the Yang system, we need to drain the event to an external system, and this draining event process is done using a loop. If an external event is not responding, then the Yang system will fall into an infinite loop. So hang fix can enable the system to jump out of the draining loop, and however the remaining events are not flashed. there is a resource manager on the young system side, and if the events are not flashed, then it cannot enter into standby system for later execution. So this implies that the hang fix cannot fix the hang bugs on the stateful systems.
I see. Okay. So we have time for one more question. If there are any questions, please type them in. In the meantime, I'll ask you one more. So can you tell us a little bit about bugs that may be transient? So for example, because I think that your system relies on collecting a stack trace in order to study the bug and correct it and detect it. So can you tell us a little bit about bugs that may be transient, so they're harder to reproduce, which can be pretty common in production systems?
Are you asking about what kind of bugs are harder to reproduce in production system?
No, I'm saying, so if you have a bug that is not constant, it's a bug that happens only in certain types of cases. So your system relies on collecting a stack trace to reproduce the bug, right? In order to study it.
Right.
If I understood correctly, right. So if you have a transient bug that may not happen all the time, how do you reproduce it?
Oh, we have not considered this problem before, and yeah, it's a good point, and we should consider about it. Yeah, currently our future work, we are also involved. If we cannot collect the stack trace, then how to pinpoint the exact root cause function? So I will definitely consider your question, your concern in the future.
All right, great. Any last questions before we move to the next talk? Let me check Hula one more time. There's a question. So were you able to submit the fixes generated to developers for review?
Sorry, can you repeat it again?
Yes, so they're asking, were you able to submit the fixes that your system generated to the developers for review?
Yes, we submitted the fix for the of the 28 open bugs to the bug repositories. However, it takes a long time for the developers to check the patches and pass all the unit tests. We have checked that till now there are several bugs. I observed that 2 or 3 bugs are fixed with our patches, but the remaining ones are still open.
Okay, great. Thank you for your talk, and congratulations again on your paper. And we'll move on to the next presenter.
Okay, thank you.
Let me pull up your bio 1 second. All right. So our next paper is presented by Ting Dai. He's a research staff member at IBM Research. He graduated from North Carolina State University with a PhD degree in computer science, where he was supervised by Xiao Hui Helen Gu. His research focus is cloud computing and program analysis. So let me share my screen and then you can start. Whenever you're ready.
Okay, thank you, Christina, for the introduction. Hello, everyone. My name is Ting Dai. I'm going to briefly talk about our work. To refresh your memory, if you have the chance to watch my full presentation or read our paper. Otherwise, I hope my 3 minutes lightning talk can give you some ideas about how to automatically detect risky scripts in infrastructure code. Modern IAC tools have their own programming paradigm to write infrastructure code. For example, YAML for Ansible playbooks and Ruby for Shell cookbooks. They also support embedded scripting languages such as Shell and PowerShell to manage the infrastructure resources and interact with applications to execute the automation procedures. Risky patterns in those IAC embedded scripts introduce bugs and expose vulnerabilities. For example, the example commands as remove partition drive-c or remove or rm-if/ will remove the disk drive could result in business disruption when they are invoked in the production environment. The consequences of the risky IAC embedded scripts are severe and sometimes disastrous. For example, in 2017, the Amazon S3 service became unavailable for 5 hours with financial loss of $100 million due to a removal command invoked by a system administrator who inadvertently removed a large set of servers. Existing infrastructure linkers such as ANSYS and PubliLink lack the capability of checking IAC embedded scripts, while generic script analyzers such as ShellCheck and PS script analyzers support script format and syntax checking, which has brought to light the opportunity of conducting static checking over those IAC embedded scripts. However, applying those existing generic script analyzers directly on checking infrastructure code can result in both false positives and false negatives. Moreover, without correlating the moreover, without correlating the identified issues with the risky behaviors, users have no understanding about how the risks manifest in the production environment, what the potential business consequences of those risks have, and how severe those negative consequences are. Next slide, please. Thank you. Bridging the gap between generic script analyzers and business consequences in order to deliver an accurate checking framework gives us the opportunity and motivate our work. Our paper proposed an analysis framework which takes an infrastructure code repository as input. It first generated a structural representation trees for the repository. By traversing each tree, it composes script contents by removing the template renderings after identifying that the infrastructure code invokes script executions. Because we have observed that the template rendering is popularly used in the infrastructure code. So that's why we have to remove the template rendering when we compose the scripts. So after passing the composed scripts to open source script analyzers, in the paper we use ShellCheck and PS script analyzer. Our framework receives the checking results with issue IDs and the line numbers of the composed scripts where the issues reside. To satisfy configurable business compliance requirements, our framework then assigns the severity levels and the potential impact for each identified issue based on a predefined assignment rules retrieved from the knowledge base. Our knowledge base is generated by empirically studying all the rules from open source script analyzers. Our framework then maps those issues to the corresponding infrastructure source code lines before returning them back to the user. In the paper, we have implemented secure code using our analysis platform to identify the risky scripts in Ansible infrastructure code, which is Ansible playbooks. We integrate secure code with CI/CD pipeline deploying IBM services using Travis CI. We test secure code in 45 IBM services community GitHub repositories. Our results show that secure code can identify more than 3,000 issues in minutes from the 45 repositories, which contain about 1,500 automation files. Secure code is accurate with 116 false positives. Our evaluation and also our user experience show that secure code achieves 2 to 5 times throughput improvement compared with other approaches. Moreover, secure code can identify 2 to 5 times more issues than other approaches. So to this end, I'm happy to take any questions now. Thank you.
Great, thank you. Let me go to Huva first. Any questions there? Yes, we have one. Okay. So during variable reformat operation, where the variable values are recursively substituted, there could be a bug in the script which could make this recursion go on forever. Do you have checks against it?
Yes. So we have a loop or a recursive function that is recursively to do this kind of variable replacement. So we will stop whenever 2 conditions. One is when we have extract the real value from of this variable, or when we have found that this variable after 2 iterations, the the command or the script is the same, stay the same, which means that this variable cannot be further replaced.
I see. All right. So while we're waiting for questions to come in the Zoom Q&A, let me ask one. So one question I had is, how easy is it for an operator to adjust the severity of an issue?
What
Can you adjust the issues that you track at runtime?
Sorry, I didn't get it. Sorry, can you say that again?
Right. So if an operator realizes that an issue should be considered more severe than is that something that you can adjust in your system?
Oh yeah. Thank you. So so our knowledge base is actually configurable. So currently we contain all the rules or the checking, or you can think about that as code patterns extracted from the open source script analyzers. But those rules are all configurable because users, we have different kind of fields. Users can customize their own knowledge base. They can either to exclude some certain rules, or they can change the severity levels, etc. Or they can add more rules if they want to.
Okay, great. More questions? Let's type them into the Zoom Q&A. Okay, let me ask you what I asked the previous speaker as well. What are the limitations of this approach? What are some cases, some issues that you are not able to detect?
So the issues that is we currently highly rely on the open source script analysis. So because we you can think about that the novelty or the new things we propose is on a framework to analyze the infrastructure code. However, we highly rely on third-party open source script analysis to check those rules, right? So for example, like what you said before, if some certain rules, for example, like some kind of specific security attacks, like copy on write, like dirty cow, this kind of attacks, or some kind of form or fork bombs, those kind of things are very hard to detect. So it has to use some kind of dynamic approach. We cannot detect those specific vulnerabilities or bugs. Then that's the biggest limitation of our work. However, in IBM, we have keep continuing to implement the new functionality or checking rules in secure code, because we currently focus on specific different kind of applications. For different kind of specific applications, they have some kind of specific set of rules that, or set of commands, I think, as malicious or destructive. So that is something we want to make secure code as sound as possible, but it's impossible to detect every issue. So that's an ongoing work, and then maybe also we'll try to minimize our limitations. Thank you.
So maybe you can tell us a little bit about your future work while we're waiting for more questions.
Okay. So the future work, I think that is, so one thing that I said before, the secure code is a pure static analysis tool. And then we highly rely on this kind of third-party script analysis to do this kind of checking. And another thing that is we are going to do for secure code, that one thing I have mentioned before, that is we're going to extend the rule sets of the secure code to help us to do more checking. So another thing that is secure code is an implementation on our current framework, analysis framework. However, our analysis framework is supposed to support other IAC tools. So even though in IBM, we highly rely on Ansible to do this kind of using Ansible as an IAC tool to do this kind of automation procedures. But in other companies, or if IBM has this kind of internal demand for using some other IC tools, for example, like Chef or Puppet, then it is also feasible to implement this kind of checking ability, checking the risky IC embedded scripts in Puppet or in Chef. So that can also be our future work.
Okay, very good. Last chance for questions. Check who again. Okay, let me ask one last thing.
Mhm.
So you have to, so the order of script execution matters, right? Can you tell us a little bit about how you infer the order?
Infer, okay, so I want to say that the we in the paper we propose structural representation trees that gives us this kind of top-down ordering, or you can think as left to right ordering. It's the same thing. It's just if, how you're going to orientate the tree. So it actually mimics the execution steps of the infrastructure code. Or I can use the Ansible playbook as an example. For example, like there are two type of orderings in the Ansible playbooks. One thing is in a single file, every execution is from top down, from line 0 to line n, right? So in this order. So we keep the same ordering when we generate this kind of SRT tree, and then to mimic this ordering steps. And another thing that is sometimes we have found that a playbook will execute another playbook. For example, like you can use import, include this kind of keywords, and then we know that this kind of ordering can also be inferred based on this kind of keywords. Then we know, okay, we need to execute these steps from playbook 1 first, and then to analyze the remaining steps from playbook 2. So that is the how we infer this kind of ordering.
Great, thanks a lot. So if there are no more questions, let's thank Ting again. Thank you very much for your paper and your talk.
Thank you for having me.
And we'll move on to the next presentation. So Jason, when you're ready, please unmute yourself and turn on your video. So our next speaker is Jason Teo. He's a 5th-year PhD candidate at UCLA, working at the intersection between big data systems and software engineering. His research primarily focuses on improving developer debugging experience within big data systems, and recently he has been looking into the intersection of big data and machine learning. Give me 1 second to share your slides. All right, hopefully that's showing up so you can get started.
All right, thank you for the introduction, Christina. Hello, everyone, and thank you for coming to the lightning talk on influence-based provenance for data flow applications with taint propagation. To give a quick recap of the recorded presentation, we presented our tool, Flow-Debug, which is an enhanced provenance debugging tool. So the key debugging question that Flow-Debug and many other provenance-based systems attempts to answer is, given a suspicious output or outputs, what are the corresponding inputs? Compared to traditional provenance techniques, Flow-Debug improves the provenance precision through its key insight of taking into account the user-defined functions, or UDFs, and the specific input contributions through these UDFs. So Flow-Debug is based off two mutually compatible techniques, the first of which is UDF overtainting on the left-hand side. And UDF overtainting automatically modifies data load statements to use a custom instrumented data type, which we use to internally track UDF control and data flow operations that propagate provenance throughout our instrumented data type objects within the Spark execution graph. So these are operations that may come from numeric operations such as addition, or also kind of string operations such as a string parsing function. On the right-hand side, we have our alternate approach to UDF overtainting, which is influence functions. And our influence functions API is designed to be very fine-grained, or very flexible with respect to how provenance is captured. So we open up a similar to the Spark API, the Spark's combined by key API, we open up a combiner like influence function API that allows users to define what kind of provenance they're interested in capturing for individual aggregation operations and key groups. Because it's designed to be flexible and easily configurable, the influence function API is also dependent on how developers leverage their own insight and knowledge about the application to define those influence functions. If you go to the next slide, please. So giving a quick recap of the results that we determined from flow debug. First off, we have this diagram, which is actually an example of one of our benchmark executions. And without going too much into the detail of how the diagram itself is constructed, since that is discussed in the recorded video, we have on the screen that we've effectively combined an influence function on the left-hand side, the bottom one influence function. We've combined that with UDF-aware tainting. And the result is shown in green, which represents our input trace for a particular output record, compared to this traditional data provenance technique that we evaluate flow debug against, which is shown in gray. So even without going too specifically into the details of how influence functions and UDF-aware tainting operate for this particular example, we can see that the number of records returned is going to be much smaller and much more precise than a traditional data provenance approach. And this is actually reflected a little bit in our evaluations when we compared flow debug against a traditional provenance implementation, and both of these were done on top of Spark. We observed that flow debug actually achieved 15 to 100% more precision, and this is in absolute values compared to the comparison that we used, which was Titian. In practice, we also found that our instrumentation or instrumented runs ended up being much faster, 5.4 to 8 times faster when we were using influence functions. The overhead when we were using UDF-aware tainting was actually a little more complicated, so that's discussed both in the paper and the recorded presentation. I'd be happy to answer any questions about that as well. And as our final result, we decided to take a look at the time it takes to actually trace or identify specific inputs for a given set of outputs that a developer determined was suspicious. And in this practice, we found that flow debug was able to achieve much faster input isolation on the order of 12 to 73 times. I think that about concludes it for my lightning talk. So I'd be happy to look at to answer any questions that people may have now. And I think I saw a few on Huva as well.
Great, thank you. So while people are typing in their questions on Zoom, let me check Huva. I think we have a few questions.
Okay, I can take a crack at Preeti's question first.
Okay, let me just read it out for the. Yeah. So since Titan uses traditional provenance, it's an exhaustive search. Hence, in the slide on accuracy comparison, how is it that flow debug performs better?
So this is a great question and it's a very astute observation. You're absolutely correct that Titian does use an exhaustive search approach. I think there's a small clarification I need to make here, which is that in regards to accuracy, our evaluation of flow debug is actually broken down into two parts. There's a precision and recall component. With Titian, what Titian does is it achieves very high recall. Because it's doing this exhaustive search, it's guaranteed to give every single relevant input record. And the contrast between Titian and flow debug is primarily on the aspect of precision, which is of the returned input records, which of those are actually relevant to the output that we're interested in debugging. So in terms of recall, flow debug actually ends up matching Titian. They both achieve essentially perfect or 100% recall. But our results for flow debug show that flow debug can actually significantly kind of prune down the input trace size and remove many of the irrelevant input records that Titian is returning. Fundamentally, this is because Titian operates at an operator level rather than kind of the UDF semantics. So because it's only looking at the operator level for some simple aggregations, for example, a min or max aggregation, Titian would still return every input to that aggregation. Whereas flow debug is able to go this little step further and say, okay, well, we only need to identify just these single minimum or maximum input records that correspond to that particular UDF.
Great. So one more question from Huva. Yusun says, excellent work. The flow debug paper, I'm assuming, has modified the original UDF to avoid the over-approximation and combined it with influence-based provenance to improve precision. Can you explain more about how the influence-based provenance method is extended based on the original Spark API? It seems that it combines some observed patterns.
Sure. So within flow debug, we have a sort of modified or mirrored Spark RDD API that is specially configured to internally track provenance. Our modified version of the aggregation APIs, which our influence functions are used within, they essentially allow for an optional influence function argument. And this influence function argument, as we presented the interface earlier, It consists of operations such as an initialize, merge value, merge function, finalize method. And all of these arguments are effectively reflected in the original Spark combined by key API as various function type arguments such as create combiner, merge value, and merge functions. So at a high level, what the influence functions are doing is they're effectively mirroring these input arguments to Spark's native combined by key operations. And when we actually run our instrumented program, we're merging the Spark application logic with these influence function logics to simultaneously capture provenance while executing the application. In terms of, I think the question mentioned a little bit about observed patterns. So there's also a few common patterns or influence function behaviors that we observed when we were running our evaluation benchmarks. So for example, we noticed that some programs could be easily debugged if you just retain maybe like the top or bottom 5 values. And in that aspect, we kind of abstracted out some of these patterns and implemented them as predefined influence functions that people can leverage.
Right. One more question from also from Yusun on Hoover. So how flow debug precomputes provenance or input traces during runtime? Which means how does the flow debug know which result to precompute?
Okay, so I think I maybe need to ask a quick clarification. Is the question referring to specifically how flow debug knows what kind of provenance like strategies to apply, or is it more of a question of how do we know which outputs are of interest when we're applying or capturing this provenance information?
So we have you on the call. You, if you want to clarify, raise your hand and I can unmute you.
Okay, well, I could kind of take a crack at answering both then. So as far as what provenance strategies we use within flow debug, that's mostly developer configured. We provide the UDF-aware tainting as kind of an automatic or easily adopted approach, where the developer really just needs to modify a data load statement, and UDF-aware tainting can theoretically handle the rest of the application. On the other hand, we also offer the influence functions, which are much more developer heavy, and they require developer knowledge and insight to actually configure how these influence functions should reflect the provenance capturing of the application logic. On the other hand, there's also this question of how do we know which output records we want to capture provenance for? And at the current moment, flow debug actually does not discriminate between the outputs. So flow debug during its instrumented run it's capturing provenance for every single output record that is being produced. And this has a nice benefit in that if you, for example, run an instrumented run and you don't necessarily know which outputs specifically you're interested in debugging, you can run multiple input traces after that single instrumented run, and you can analyze many different results to kind of compare and contrast. It theoretically is also feasible for a developer if they know exactly some subset of inputs that they're interested in investigating. They can configure their influence functions to also kind of parse out irrelevant provenance information during the instrumented run ahead of time.
Okay, great. I guess let me also ask one while we're waiting for more questions. So this might be in your paper, but I may have missed it. Can you tell us a little bit about the overhead over just baseline default Spark without any instrumentation?
Yeah, so I'm quickly referencing my paper because I don't know the number off the top of my head. We did do a baseline comparison against Spark in terms of the instrumentation overhead, since Spark doesn't actually support tracing. And in practice, we actually found that there was an overhead ranging between 0.4x to 6.1x. So the 6.1x, if I remember correctly, is largely from our UDF-aware tainting approach, which is going to be a little more kind of heavily instrumented. In contrast, the influence functions can be configured to be very lightweight, depending on what kind of use cases there are. And that's where we're seeing, for example, the 0.4x.
Great. And then I guess one more clarification, unless there are questions, no? So do you support the RDD-based API of Spark? And do you support like other related frameworks like MLlib or PySpark? And how difficult would it be to extend it to them?
So that's a great question, especially because Spark provides so many of these kind of extended frameworks. Right now, flow debug primarily targets the base RDD API. And the goal behind that was because this is kind of the fundamental building block for the rest of the tools. I think in terms of extending to these, for example, like Spark MLlib or SQL, I think the approach is certainly applicable, but it would require a little more kind of extension within the Spark libraries. I think fundamentally many of these libraries do ultimately kind of translate down to Spark RDDs or data frame conversions. So if we modified that particular kind of translation process to leverage Flow-Debug's APIs rather than the Spark native APIs, that could be one step towards adopting or supporting more of the extended frameworks.
Great. Any last questions for Jason? Okay. If not, then thank you very much again.
Thank you very much for having me.
Presentation. And all the presenters will be available after this session near their poster. So if you have follow-up questions, feel free to go and find them in the Gather platform. All right. So then we'll move on to the last presentation of this session. Rasha, when you're ready, please unmute and turn on your video, and I'll introduce you. So our final presenter is Rasha Fakeh. He is a PhD student at Dresden University of Technology in the Systems Engineering Group. And his research interests are the modeling and analysis of dependable and distributed systems. So let me share your slides, and then you can start. Okay, when you're ready, you can start.
So, hello and welcome to my talk, which is about building a trusted list primitive to be used with untrusted environments such as the clouds. A trusted list can be defined as a list designed to maintain its correctness properties even in the presence of a privileged attacker. To build a trusted list primitive, we need to handle the following attackers who might try to violate the list correctness invariants. An attacker might attempt to manipulate the node's code and data to make the nodes behave incorrectly. So we use Intel SGX and execute applications inside enclaves. An attacker might also try to change the value, the clock value. So in TList, we use enclave interval timer to tolerate any value modification and to track the list terms at the grantor and the holder sides. How we do this? We use TSC, which is timestamp counter, as our trusted time source, since it is not mediated by the OS, which means that when we read the value, the OS cannot delay the response. But unfortunately, the OS can still change the value and the frequency, but luckily can do this only during interrupts. So we need to detect interrupts, which we do by checking the SSA structure value. We set it to a predefined value, which will be overwritten if an interrupt happens. To estimate the duration of an active list, instead of absolute time, we count intervals, so the time difference. For interval counting, we consider intervals counted inside the same epoch. An epoch is the uninterrupted period of an enclave execution during which we know that the clock cannot be tampered with. A third type of an attacker might try to violate the list correctness by changing the TSC clock frequency, so the tick rate, to make the clocks tick faster or slower. So we need to detect the change in the TSC counter rate by comparing it to a sequence of RD rand instructions, which the OS cannot change its frequency. And we abort execution if the results are out of the scope of architecture-determined bounds. Why do we need 6 instructions? Because the latency of the RD rand instructions is by itself non-deterministic. So we have to consider the standard deviation. So we use 6 instructions. And 6 is a trade-off between the verification cost and the accuracy. Now, this is done after each interrupt detection. Next slide, please. Another attempt of an attacker to break our list correctness is to break the atomicity of the routines we use. He takes advantage of the time of check to time of use variability in operations such as interrupt detection in enclave interval timer or in timer frequency verification, or he can try to break the atomicity when checking the valid list and submitting the computation results that require the valid list. So our defense against this is to use transaction system call interface. So we use Intel TSX and execute the routines and instructions that require the valid list in an atomic way inside transactions. So with these approaches, we have shown in our paper that T-list is safe to use even if we have an attacker who tries to manipulate the clocks. And a timer manipulation in the worst case results in a performance loss. Additionally, it is fast, so imposes minimal performance overhead, and it is usable since we provide easy-to-use generic API. Thank you for your attention and any questions.
Thanks a lot, Rasha. So let me check Huwa first. It looks like we don't have any questions on Huwa. Please type in your questions in the Zoom Q&A, and in the meantime, I can ask you a question. Okay, so can you tell us a little bit about the overhead of frequent checks? What is the performance impact of this process?
So it depends on the application, but or the interrupt rate, but it's around, it's almost 5%. It could be up to 25% if the interrupt rate is high. But in the normal interrupt rate that we could find in Linux, it's about 5%.
Okay. And then can you clarify a little bit how the communication between the grantor and the holder works? So they're both running in SGX enclaves, correct?
Yes, so the communication is done through UDP sockets, and it's encrypted using AES GSM encryption.
Mm-hmm. Okay, great.
And they could both be in the same machine or different machines, but yeah, the standard is to have them in different machines.
Great, thank you. Let's wait a little bit for more questions to come in. I guess I can ask you the question that I asked all the previous presenters. Tell us a little bit about the limitations of your approach and what comes next.
So the limitations of this approach, it's specific. So the routines that we use is specific to Intel SGX because it's architectural solutions. So if we try to apply it on other TEs, then we might not need these complications that we already have in this approach. So it might be simplified, but how much simplification could be done for the timer reads or for the frequency verification, this depends on the TE itself. So if we transfer it to another TE, we might need to adapt this. Depends what kind of secure time sources these other TEs provide.
Great. And what are the next steps for this work?
So I think the next step is to try to see how applicable is this to other TEs, and yeah, and whether we need or we could find other ways to simplify the routines even in SGX. But I think the simplification of these routines depends on yeah, if we have extra hardware that would simplify the TSC frequency reads or verification or the value to know whether the OS has changed the clock value or not. So it's just a way either to simplify the current implementation SGX or to try to find what is the how much this is applicable in other TEs.
Okay, great. So since you mentioned extra hardware, what would be your wish list for hardware features that would simplify your work?
So we could think of like our problem is that we want to ensure that the OS or the attacker, regardless, did not change our value and he didn't play with the frequency. So for the value, we could see if, for example, if we have an extra register that would say every time the OS changes the clock value, like by setting a new value in it, then we might have an increment for this register. So for us, this would simplify stuff because then we have to read only this value, and we can, when we start the execution, we would read the current version of this register, so as kind of version, and we can simply check this register, and if this value is not changed, then we know that the OS did not change this value, the clock value. For the frequency, it would be great if there's a way that the underlying hardware would or software would inform, or there's a way that we could read directly the TSC frequency or whatever timer we use, like directly access what is the current frequency, which is not available by the current x86 architecture.
All right, great. Thank you for the answer. So last call for questions. All right, so Brian asks a question. Since you mentioned that the future work entails adapting to different TEs, do you think hardware vendors should provide a more general, unified, or higher level of abstraction with regards to security?
Can you elaborate more? Like what kind of like generalization you're talking about? Because in our case, it's in order to use these correctly, we need a trusted time source. So it could be different between an architecture to an architecture in another architecture. So if we could find that time source, regardless what is the architecture that we're using, then it's enough. So it's not enough just to provide a time source, because if architecture would have its own time sources, but we need to ensure that the attacker / OS cannot modify its value or frequency without we as an application not being able to notice this.
I see. Okay, well, Brian, if you have more clarifications, you can find Rasha close to her poster after this session, so you can discuss it there. All right, any last questions before we wrap up this session? Okay, well, let's thank Rasha again for her great paper and presentation, and thank you to all presenters. This is the end of this session. Next is a 1 hour period where you can interact with people in the Gather platform, and then we'll resume here at 1 p.m. Eastern with the next session on accelerating machine learning. Thanks, everyone.